Hello, Elvis. Hello. Hello, Elvis. Can you hear me? You are all welcome to our week four session as we continue with our bootcamp. You are welcome, Edu Jenfi. You are welcome, Lisa Robert. You are welcome, Fortune Marvin. You are welcome, Frank Kachu. Nice meeting you. I think yesterday Edu Jenfi was here with us for our week three session, which we talked about supervised learning models, where we have Miss Glory leading us through the session. Today, we continue with our session, and in the next few minutes, as we wait for our colleagues, as we wait for a resource person who is joining us soon, in the next 2 or 3 minutes, I want us to exercise patience as we wait for him and also our colleagues to join us. I would like us to share the link to our friends, share the link on our statuses, share the link in our groups to for our colleagues to also join, for our colleagues to also um, partake in this session. So if you are here, you can share the link on your WhatsApp status, you can share the link in any group that you are in on WhatsApp or Telegram so that others can also participate and learn from this bootcamp. So thank you very much. This exercise patient as we begin very soon, the next 2 or 3 minutes. Hello everyone. This is, if you can hear me, I want to see you react to my voice. If you can hear my voice, please react. Okay, I'm seeing Elvis. I'm seeing Edu Jenfrey. Please, if you can hear me, can you react? Can you react? Let me see your reaction. If you can hear me. Okay, I'm seeing First Marvin. If you can hear me, please react. If you can hear me, please react. Okay, I'm seeing Miss and Robert. Okay, now I'm seeing from Kachu. Okay, and our resource person also here with us. So without wasting my time, thank you all for joining once again as we continue with our bootcamp. Today happens to be our fourth session, and our resource person is none other than Mr. Eric Ayitey. I want us to react as we welcome our resource person to take us through this session, which focuses on advanced models and ensembling basics. So I want us to also get ready with our laptops and notebooks as we take notes and also as we practice. So be ready with your laptop, be ready with your notebook, because from here, as we continue with other sessions, we'll be making practice of what we have learned so far, and also there will be challenges for us to solve in order to award participants who bring solutions to something that to set up for the boot camp. So I'll give the platform to Mr. Eric Ayitey, who is here with us to take control and lead us for today's session. So let's welcome Mr. Eric Ayitey. Mr. Eric Ayitey, please, if you are there, you can take control now.
I think his network is on hold kindly. Probably a call has come in on his network, but he should join. He should speak soon. And
Hello, everyone.
yes, hi. We can hear you. Hello.
All right. Elvis, please confirm if you can hear me. Sorry
Yes,
for the.
please. Yes,
All
please.
right,
Yes,
all right.
please. We
So,
can hear
Yes, please, we can hear you.
good evening, everyone. And then, I must apologize for the delay. Actually, it was raining here for a while, and then it's made the network messy. But then we can still have this meeting and then leave without anything. So please bear with me if my network fluctuates at a point, but I'm trying to have the most stable network I can have for this session. So please let me know at any point when you lose me. Just don't hesitate to draw me back. I'll go back and then talk about whatever you lose or you missed me on. Is that okay? Oh,
Yes, please.
I think one thing that will make this meeting a success for all of us, let me iterate is your reaction or your responses. Um, as an instructor, one thing that motivates anyone who is speaking at one point in time is getting to know that whoever you are speaking to, whoever you're addressing, is hearing you and then gets along with whatever you're talking about. And the only way that can work for you and I is when you unmute and respond when necessary, and then when you react as well. So please feel free to react, send all your interesting emojis, and then ask your questions as well. I hope we are on the same page. Oh, I just said something and still okay. Two people have reacted. That is good. So just going straight into what we have for the night. I think I must say Elvis hasn't been fair with me. He hasn't been fair to me in a positive way, but it's good. I mean, he didn't invite me to all the 3 sessions, with the exception of this. So it's fine. I missed out on all the 3. I even got to realize the last session was like yesterday or a few days ago. I really don't remember. But it's all good. So I'm of the assertion that we know a little bit or even much more than I do with regards to machine learning. So this is going to be a very simple meeting for all of us to share our idea on what we already know. And then if possible, add up to what we already know. That is basically why we are gathered here. And this evening, we are going to look at advanced models and assemble basics, right? If I got it right. Trying to connect with my laptop so that I can share my screen. I think I have something little to present on. So yes, we are going to look at advanced models and assemble basics. And basically our focus point is on how to improve our performance and generalization, all focused on machine learning basically. So if we are all going to share our knowledge, and I think I need to know a little bit of what you do, what you know with regards to machine learning, and then we can take it from there. So basically, when we talk about machine learning, what comes to mind? Who is willing to share something with us? Machine learning or models in machine learning? Anything at all you want to share with us with regards to machine learning? At least let's know we have some foundation to build on. Anyone willing to share with us? Elvis is not part. I don't think Elvis should be part of this. Any other person? Oh, no one is willing to share. That's fine. Okay, do JMV. Do JMV, we are with you. Yeah.
Okay, so from what I know of machine learning, it has to do with building programs that
Okay.
that accept data, and then that accepts data to improve upon themselves, so that they'll be able to make predictions so that they'll be able to make predictions about other data, and there are so the program that a machine learning engineer will build is what is called a model. And then the types of the systems of machine learning, that's the supervised learning, unsupervised learning, and reinforced learning. But we spoke of supervised learning. And in supervised learning, you feed the model, or you give the model data that we call it labeled examples. So it's like you give it the questions and the correct answers. So with that, the data will have to find the relationship between the questions and the answers themselves. So after that, then to be able to make predictions or give answers when you give it only questions, that's the supervised learning. So yeah, that's my idea of it.
Hello, Mr. Eric.
Hello.
Okay, so please, Adujenfi has shared with us
Oh,
what machine
all
learning
this while
is.
I was talking to myself. That's sad. So I said thank you for sharing Edu Jenfi, and we are looking at advanced models.
Thank you too.
All right, and we can't look at advanced models when we don't know what a model in itself is. I mean, before we advance to something, we should know what the basics is, and then we can move on to what we should look out for in the advanced version. So basically, that is what we are going to do for now. So I think let's move on to me sharing my screen, and then you can confirm if um, my screen is visible. Please, is my screen visible? I want to believe so. Hello. Can anyone confirm if my screen is visible?
Yes.
Okay, okay, thank you. So I think we can proceed, right? If my screen is visible, then we can proceed. So talking about model, like Edu Jenfi right said, we need to know what a model is from the onset before we can proceed to an advanced model. So a model in itself is basically defined. I don't know how you define that, but from my perspective, I define a model as simply a nurtured algorithm for a machine learning project. So it's a function that literally takes data in, like Edujenfi said, and it looks for patterns during the training phase of building that model. And then based on this pattern that it finds, is able to make predictions on new data that it has never encountered or it has never seen. But then the reason why we are looking for it to extend our knowledge to an advanced model is that a single model can make mistakes. And you all bear witness to the fact that it is true, you can't even rely on one source of data to make your predictions. Let me give you a very clear example. Um, as most of us have either in school or our graduates. I mean, one way or the other, you went through the school system. Now, what happens is, even in the exams or when you are too confused or you are not so sure about an answer and you want to find out from a friend, trust me, you barely take an answer from just one person and proceed. Unless maybe in the rare case you don't have time. So, I mean, whatever you get, you just proceed with it and then we are good to go. But in the case where you have enough time, you want to take answers from, I mean, three brilliant students you can confirm for yourself. And even with the answers you get, you look out for, okay, maybe I always said A, and then I'm saying B. And whoever introduced me, is the name David or Daniel? I really didn't get that. Maybe he also says A. So that keeps you wondering, okay, now two people are telling me A and another person is telling me B. So based on that, you've advanced the answer to your question by getting more than and one answer. So based on that, you can make your comparisons and you can actually settle on one answer you want to go with. So that is basically what Ensemble Basics or Advanced Model here we are talking about works. So we understand that a single model can make mistakes. We will look at some of the mistakes that these models can make. So how do we
go beyond these mistakes that the models can make. So all we need to do is look out for other models, train them with the same data. So perhaps the mistake in model 1 might not be the same mistake you will encounter with model 2. Neither will you encounter any of these two mistakes in model 3. So over there, you're able to put all the possible mistakes together for an ensemble basic or an advanced model. Oh, look at these individual models. Look at the mistakes that each one of them is encountering, and then move past that mistake. So if there's the mistake, how do I tackle it so that I don't do the same mistake? Perhaps the first model was biased. So how do I refine that I'm not being biased? That is how the advanced model is going to work. Maybe this first model was also having a very high variance in the case of an overfitting training data. So how also do I adjust the variance so that the variance is not too high? So this advanced model is more like learning from the mistakes of your previous models to improve on its outcome. Please, are we on the same page? I think because I'm sharing my screen, I'm not seeing the reaction, so I would prefer the responses, if that is fine. Are we on the same page, please?
Yes.
Okay. Any question to this point, or we can make progress?
No questions.
Okay, then I think let's continue then. So I've talked about the essence of using or considering advanced models and what we are going to look out for today. So I've talked about the fact that single models make mistakes, and then different models also make different mistakes. So combining these unrelated errors in total will reduce the total error that the advanced model is going to encounter. So in the end, we are looking at the combination of diversity. So you have different models and then you are combining them. So diversity plus this combination is presumed to give you a better generalization. Let me take it again. So having diverse models trained on the same data, making different errors, and then now bringing these models together under an ensemble is assumed or presumed to give you a better generalization, because an ensemble works best when its individual models are reasonably accurate on their own and as well make different mistakes. So this model is right with one thing, however, makes mistakes with another thing. So once you have this individual mistakes and then the variation and everything, putting them together, you can draw a simple conclusion to that. So let's look at the real world scenario. Perhaps you go into the hospital. I don't think the doctor would look at you and then just because your temperature is very high, say maybe you have fever or something. Not because that is not a symptom of fever, but because that is not enough information to actually arrive at a final diagnosis. That is basically how this advanced model of machine learning does. So even though he has seen or the doctor has seen that your temperature is high above normal, the doctor will actually confirm that with the thermometer, also request for laboratory in most cases. So the tests of your lab results is actually going to affirm or confirm whatever the doctor is expecting. What if the doctor was wrong? Then we move on to another diagnosis. So this variation is what is going to help these advanced models give you the best answer or the best outcome. So what are some of these variations we are looking at here? So let's look at the bias variations here. So the variations we are looking out for here, we are looking out for first the bias variance trade-off. So this is basically the backbone of everything we are going to do here. Okay. This is everything we are going to do here this evening. So we are going to look at how these models come together under one ensemble and then how it handles the bias and then variance trade-off. Come to think of it, the bias is from a different model and then the high variance from another model, bringing them under one umbrella and then expecting to treat this very, very well. So look at this simple formula that I have here. So a square of your bias from that model plus the variance you're encountering plus irreducible noise should be equal to the expected error. So machine learning models are almost every time broken down into these three parts: the bias, the variance, and then irreducible noise. These are most of the time the issues you encounter with model training. When you are training a model, it's either there is going to be bias, and all this stems from the data set is being trained on. All this stems from the data set is being trained on. I don't think I have to take us back to training a model because we've advanced past that. So in the case where the data this model is being trained on is biased, then your model is definitely going to be biased. I think we've had multiple examples of this. And the recent one I think I saw had to do with Amazon, when Amazon decided to switch from a human recruiter to uh, a machine, or let me say ML recruiter, basically an AI recruiter. So the data this AI was trained on had a lot of male resumes. So at a point they realized that almost all the people or the resumes this AI was predicting to have done better and then should proceed with interviews were mostly male. Like you would have less than 5% of females in there. But then when they check the resumes for themselves, they realize that that is not what is supposed to happen. And they realized this was because the model was trained on a biased data. So it felt tech was basically open to more guys or more gentlemen than ladies. So it wasn't giving ladies equal opportunity. And then we can encounter this in many scenarios. So bias is one thing that really stems from training our models. So when there is bias, then there are going to be errors in your prediction. Basically, errors in your prediction. And then we look at the variance. So bias, basically, let me say, talks would look at um classification, basically. Yeah, classification where your model has direct answers and all of that. It can also work in regression, but rarely, because with regression you kind of leave it to find a pattern for itself. And then that is where variance also comes in. Most cases, you experience this variance when you are dealing with models that are going to predict numbers or numerical results. You realize that your expected number and then the prediction, I mean, the variation is that wide, all stems from, again, your training data set. And there is no way your model can also be 100% accurate. I think anytime you evaluate your model and then you realize you are getting 100% accuracy, you should know that that is not possible. There is something wrong somewhere, either a data leak, or a fitting, or some of these encounters. So your model cannot be 100%, but then you try as much as possible to curb some of these issues so that your model can be a bit better or much more accurate. I think I'm working with the healthcare industry. Currently, their model evaluation is around 99.7. That is the standard. I mean, you can't send a 95% model prediction to a health facility or for health examination. No one is going to approve of that model. That is how far we've gone with model training, because you can't tell me out of every 100 people I predict, I'm going to get 5 of those predictions to be wrong. And that's like killing 5 people out of every 100. And that's something that is very serious. It will look like a small number to you, but looking at the world population and then taking 5% of that, that's a huge number. So that is how far variation in model predictions can also affect us. So when we talk about bias, let me explain each one of them once again and then we move on. It's just the error introduced by approximating a complex real world problem with a simpler model. So when the issue is very complex, more like let me look for a scenario like, okay, the hospital scenario, that's the works, where you have a simple model to address such a complex problem, like the fever example I gave once again. The model just takes your input, your body temperature is maybe 39, 40, and then it predicts you have fever. Because the model is very basic, it takes very little information and then tries to solve very advanced issues or real world problems. So in such a case, you realize that such a model won't work out for you. You need a model that is highly advanced. And that is where people also get it wrong. Because of some of these issues, people want to always begin with advanced models. I mean, machine learning prediction, regardless of what issue that model is going to address, regardless of the data set they have, regardless of what they seek to achieve. They just go in for very advanced models to even tackle very simple issues. I think that is something that in the end isn't also going to benefit you, because simple problems require simple models, and complex or advanced problems also require advanced models. So let's keep that in mind as we proceed. So whenever you have an issue to tackle, a machine learning project to build, look at the density or the way the options or the outcome. What do I seek to achieve? And then what model address the issue best? And based on that, you know which model to go in for. You don't just get up and then maybe I need to just predict gender for a group of people, something that a very basic machine learning model can do, since it's a classification model, something a basic model can do. You go in for a very complex model, you adjust, you fine tune your data training. I mean, you are just stressing because you want to come out and then everyone will be like, oh, we used this simple model, and then you are using something like decision tree when you can use a very simple model to actually solve that same issue, because you feel that is where, or that is what proves that you actually did good. So in a case where you can use a very simple model, maybe logistic regression, maybe KNN, maybe random forest, SVM, for very simple models, you want to go the extra mile and then go and look for models that, I mean, people haven't even heard before to solve the same issue. You might end up getting the results you want, but every model handles your data differently based on the complexity of the model. Based on the complexity of the model. So let's take random forest for a classification example, and then I've given it male, female, gender as my output. And then I go in for another model that it's supposed to be solving maybe statistic issues, do a lot of statistics to do the predictions for me and all of that. And I give it this simple data. It will overfit the data because it is going to learn beyond what you expect it to. The task it is supposed to solve, that is not what it is solving. So it's more like giving a job to a wrong person. You end up not getting what you expect to get. So that is one thing we should always look out for. Look at the complexity of the issue you are handling, and then going for a model that addresses that issue basically, and then you can proceed with that as well. So I'm not here to predict models for you. I mean, based on what you want to do, you can actually explore which model works best for you. So let's proceed. So let's look at the trade-offs. So as a model becomes more complex, then its bias decreases. However, its variance increase. So there is a trade-off here. If you want to decrease bias, then we are looking at a more complex model. That is, if you are only looking at decreasing your bias, maybe your data set is biased, but looking at a complex model can help you address this bias. However, your variance would increase. And then as a model becomes simpler, its biases increase, and then the variance also decrease. So a simple model will have an increased bias and a decrease in variance. So the answers are most likely very close to whatever you expect. However, if the data set is biased, you will see that clearly in your output. Then a complex model is not entirely biased because there is a decrease in bias, but the variation might increase as well. So if it comes to maybe predicting numbers, I won't be biased. I mean, the model won't be biased, but your prediction might have quite a high variance compared to what you're expecting. And then something that happens most often is this, the overfitting and underfitting when it comes to training models. Overfitting and then underfitting. So people look out for more complex models, just like I told you earlier. And then this complex model solving a simple problem would overlearn or learn more than you expected to. So you have a high error in your training. That's what I'm saying. It's going to learn beyond what you expected to. And then when you are testing as well, you can tell. That is where you can find a model giving you accuracy of 100% because it has learned more than you expected. And then there's bias in because you want to address bias, you go in for such a model. It learns more than you expected, and then it gives you a high accuracy, and you think you've done so well. But then the problem you face will be bias in your data. If it was trained on a biased data set, trust me, we already looked at bias here. When you use a more complex model, the bias will decrease. So more like using a simple model that is underfitting, then you are going to experience bias. So in such a case, you will need a more complex model because a more complex model decreases bias. I hope I haven't confused anyone yet. if you are working with a model, let's say your data set is not your data set has some biases in. Sometimes you don't choose which data set to use for which model. You use what is available. I mean, that is a normal human thing. You use what is available. So what is available is what you're going to use. So if your data set has bias in there and you want to address the issue of a high bias, then you should go in for a more complex model. And that is what people term as, or we term as boosting. So going in for a high model just to decrease the bias. But mind you, if it's not a classification reaction, then you should, did I say reaction? Sorry, a classification model, then you should also look out for high variance, no bias. So, I mean, you can't literally get everything 100%. So once you are addressing one side of the problem, then you're actually creating a problem at the other side. So if that is what you want. And then the best option we all want is training error. I mean, you don't have error. The model learns perfectly because it is the right model for whatever task you want to achieve. So the model learns right, your test passes with less error. And then that is a perfect model. So you keep it and then you have nothing to fix. And then the issue of overfitting. When the model is not able to learn, the model is able to learn beyond what you expect, and then it gives you a high test error. That is after you've trained your model and then you are testing, the model is more like giving you everything on point. Then you should know that you have a problem to also solve. And you solve that problem by actually fine-tuning the model to learn just as you want it to learn, because your model is learning beyond your expectation. So you should fine-tune the model, not because the model is bad, but it just needs you to fine-tune it in a way for it to give you to understand what you need and how to address that need as well. Please, are you all with me? Hello.
Yes.
I hope I
Hello,
haven't I hope I haven't I haven't confused anyone yet.
No.
Okay. Okay. So we understand some issues we can encounter with building a model and how to address these issues, right? Now, let's move on to the next thing I would want us to look at. That is the bootstrap aggregation, or what we term as bagging. So this, now we are moving into the assemble basics or the assemble strategy. And this is the simplest of the assemble strategy when you focus on the bootstrap concepts and then parallel training. When I say parallel training, don't worry, I'll come back and then explain what parallel training is. So when we talk about parallel training, it is just a way of training your data set, and then you're going to sample the data set. So you don't actually sample basically like how models sample, but you sample with replacements. So that is what we term as bootstrapping. If you ever hear bootstrap, I don't know who has heard bootstrap. If you hear bootstrap or bootstrapping, that is a term under assemble strategy or bargain. Now, what we are saying is that with bootstrapping, let me just switch to that. Now, with bootstrapping, you sample with replacement. So the data set you have that you are training your model on, you create a subset out of that data. You create a subset out of the original data you have. So the subset you create out of the main data you have now becomes the data set that you are going to pick from. And then you can pick and then also replace. So whatever is left. So let's say I have a data set, entire data set of UG students, and I want to train on a model. So I create a subset of that data set where I randomly pick, but then I can always replace what I picked. So maybe I pick Elvis into my bag. That's why we term it bagging. So I pick Elvis into my subset or the bag I'm creating now. Now, after putting Elvis in the bag, I bring Elvis back again to join the number of students in the main data set. And then I still pick again. So if I need 100 individuals, that is the same way I'm going to do it. So it's possible I can pick Elvis like more than once. Are we good? It's possible I can pick Elvis more than once because I'm picking or I'm sampling with replacements. So after selecting or doing this sampling, then whatever is left or whatever is left in the data set, that's basically what we call the out of bag sample. So now I have the bag with data sets in there, and then I have what is outside. So basically, back in school when we're doing this sets and all of that, I think this is where our math comes in. So you can have the union, and then maybe you have another set. So any member that is in this set is supposedly supposed to be in the union. And any number that is not in this set is what you call the name of that set complement. I mean, you are in the union, but you are not in the set I have. So that is the same for the out of bag samples. So the out of bag samples is what you use for your validation. Now, how different this is from the basic machine learning model we know is for the basic machine learning model, it picks or it samples without replacement. So when you give your data set to the model, a basic model, the model is just going to say, okay, you said I should use 80% for training and use 20 for testing. So if I have 100 individuals in that data set, I am picking 80. I'm picking 80 and then I leave the remaining 20 for testing. If I pick Elvis into my training data set, Elvis remains there. He doesn't go back to the original data set. But with advanced model that uses the bootstrapping strategy, Elvis can be selected into the bag. And Elvis goes back to join the entire or the general data sets where we will actually pick again. So I can have Elvis 3 times represented in my SAP sample or in my bag for a bootstrapping strategy. So this is how the bagging works. You first create your bootstrap sample from your original sample. And then you train the model on each bootstrap sample. You train the model on each bootstrap sample. So ideally, you're not going to have like just one training for the model. So you train the model from the, sorry about that. So you train the model. I mean, the first model you have that you have trained, let's say in our case, we are using a decision tree. You train that model on your bootstrap sample. That is the sample you took out of the main data set with replacement. Then each data set can be different. So after the first sampling, you can do another sampling. You can do, more than one sampling. So you train a data set on the first sample, on the second sample, on the third sample. So maybe in my first selection, Elvis was in the first sample. The second selection, Elvis was in the sample again. But the third selection, Elvis is not in the sample. So the machine learning model this time around doesn't learn from just one sampled data set. It has variations to learn from. So that is the um advanced model we are talking about here. So that was what makes advanced models a bit interesting and complicated to use. So in a case where I was using a basic model, I'll just give it a data set, use 80%, and then learn from it, test with a 20. This time around, I need to create samples from the main data set. So I can create 2, I can create 3 samples from the data set. And I expect this advanced model to learn or to train on each of these samples I have. So it is able to learn very well. This time it's not generalizing whatever it's training on. It has different categories to train on. So I know when I approach this how to do it. It is able to learn better than a basic model. And then the last thing is you combine the predictions. So just like I used the example of good students in class earlier, that you ask questions and then you ask questions from more than one person, you compare the answers and you choose the best one. That is what bootstrapping helps an advanced model to do. So maybe in the first sample, I told you Elvis was there. The second sample, Elvis was there. And the third sample, Elvis is absent. Now, if you train or if you want to test the model's ability to predict Elvis, this time around, you should clearly tell that you have 2 against 1. Elvis in 2 samples and Elvis not in the last sample. So the possibility of predicting Elvis now is around 66%. So the model is not predicting based on just one trained data set, but based on multiple versions of the same data sets that it was trained on. So now it knows how to address complex issues, unlike how a simple model works. Please, any question to this point? It looks like I've said a lot of things. Any question to this point? Hello. Hello, are we all here? Hello, am I audible?
Yes, please, you are audible.
Oh, I asked a question, but no one responded. I said, are we all good with bootstrapping? Or bagging? Let me just say, but bootstrapping is a strategy when it comes to bagging. Are we all good? If you can hear me, please let unmute and respond. I want to see how many people are with us because I'll ask my questions later. Edu Jenfi, Evans, Forsen.
Yes.
Yeah,
Okay,
we are
Evans
here.
is all right. I mean, when the place is too quiet, I'm tempted to think I'm alone. So that is it for bargain. I mean, it's a strategy used by advanced models. So they're able to learn perfectly well. So you can always see here that your final prediction is going to be based on majority votes, what each of these sub models is predicting. So it's more like you are using just one model, but because it is advanced, the model in it is training sub models. So it's going to give that question to all sub models and then take the answer from them. And based on that, it is going to give you your final prediction. Majority votes, literally. And we can see that random forest is so far the model that has the greatest bargain achievement when it comes to bargain. People or developers prefer to use random forest for bargain because it takes bargain one step further. So basically, I think I've explained bargain, so no need to go into this again. So when we are looking at bargain, I don't mean random forest is the only model you can use for bargain or using the bargain strategy, but random forest takes bargain a step further. You can actually look at other models as well with respect to bargain. Now, advantages of bargain. We have high accuracy, like I said. The result is not only coming from one model, but sub-models within that model and based on highest voting. So you get to get high accurate results. And then it is also able to handle missing values or missing data very well. When you use the bargain approach, you're able to handle missing data very well. And then feature importance. So more like the models are able to tell which feature is very important in the sense that training 3 sub-models within one advanced model. So if one model uses this feature and another model is using the same feature, so let's say I have 3 sub-models and 2 sub-models are using one particular feature. Then it should tell you that feature is very important with regards to your machine learning model. Because to get 2 out of 3 models using that feature, then that should tell you something. So it's able to give you very good feature importance, less overfitting, and then it always does the evaluation based on the out of bag data set that you have. So literally just like how we do testing for other models. So it uses what is left outside the selection it did to actually select, I actually test how much your training data was able to be learned or was able to be understood well by your model. So that is that. And then the disadvantage is it is very slow to predict. You can tell because literally if you had just a simple model, you ask the question and then you get the answer. But this time it's like your advanced model now becomes a middleman, not a model on its own. You ask the question and it also goes ahead to ask other models inside it the question and then brings you the answer. So it takes the step from just 1 step to about 4 steps because waiting for answer from this model, from that model, from that model, bring them together, highest voted answer, and then that's what it brings. So it's slow to predict. And then it's memory intensive as well. So if you are running some of these models, you should consider your memory. Most people choose to run some of them using the online to Google Colab, but it's fine. You can still do it locally. Just know it's memory intensive. and then overkill for simple data. I told you earlier from the onset that look at the issue you are solving and look at which model works best. You don't always have to use an advanced model for a very simple data. So you also consider that. So that is the advantage of bargain, and then the disadvantages right there. I just hope I'll be able to touch on boosting and stacking. I mean, the three of them. If you are not able to do the live code, it's fine. I'll just share this with Elvis so that you can share this and then you can explore the live code for yourself. So moving away from bargain, then we are looking at boosting. We are looking at boosting, and boosting is said to be the sequential error correction. The most popular ensemble concept actually. Now, students mostly confuse this with bargain, with the use of sequential and then parallel distinction. So bargain deals with parallelism. Yeah. In the sense that I'm getting one thing from three different submodels at the same time. So that is everything is working in a parallel order. One model doesn't need to finish for another submodel to work, for another submodel to work. That is parallelism. They can all work together at the same time and then provide the answer as well. So that is what bargain does. Bargain trains models in parallel, but independently. So I'm training all the models at the same time, but independently. But boosting trains the models sequentially. So this is the only difference between boosting and then bargain. Bargain trains models in parallel at the same time, but they are different models. And then boosting is also training different models in the advanced model. So I think we can establish that an advanced model always has more than one submodel in it. That's what makes it advanced, basically. So boosting is training your models in a sequential order. So each new model learns from the mistakes of the previous one. So there's like the first model was biased. So the next model is learning that I don't have to be biased. Then the next, so maybe this is not biased and it has a high variance. Then the third models comes in and then it's like, okay, I don't also have to be have a high variance. So it's by so doing trying to reduce the error from the previous model. So what the first model did, I'm trying so hard not to do it or to reduce it to the best minimum I can. So that is the difference between bargain and then boosting. So bargain, we've talked about it. Boosting, I'm trying to improve upon the model. So learn the mistakes of the other one and don't repeat them. And then we continue like that. So that is how I've explained step by step how boosting works. So you train a weaker learner on the original data set. So this time you are not bagging the data sets. It's going to use the basic principle of training we use for simple models. But then what makes this model advanced is that the next model is going to identify misclassified examples or mistakes that the first model did. And then you train the next learner. So the next learner here is going to identify these mistakes and then learn from that. And then you continue the cycle for as many models as you are training. Are we good? So if you are training 10 submodels, you continue the process over and over again for 9 times, because the second one is going to learn, relearn. The third one is going to go through the same processes and all of that. So that is that for boosting. And then when it comes to boosting too, we have 3 major boosting algorithms that you can use for boosting. We have the ADA boost, or the adaptive boosting. We have the gradient boosting, and then we have the XG boost. So these are advanced models that you can use for boosting when you want to handle an advanced model. So you can go with a bargain approach, you can go with a boosting approach, or the last thing I'm going to talk about for the night, that is stacking. The last thing I'm going to talk about for the night as steps in or principles and techniques when it comes to ensemble basics or advanced models. So the third thing we are going to look about or talk about is stacking, or we put them as meta learning. So let me give you a very simple example. So assuming you are in a hospital that has 3 specialists, okay? I like talking about hospitals a lot. Yeah. You have maybe a cardiologist, you know what a cardiologist does. Basically takes care of the heart. He's a specialist, a heart specialist. You have a neurologist, and then you have a radiologist, those basically in the scan department, and you know what neurons are. So these are 3 different specialties or specialists in the hospital. And then each of them is examining the same patient. Now they each give their opinion. Then the senior consultant there is going to review all the opinions together and make the final diagnosis. Unlike in a courtroom, I mean, they are all lawyers, only coming from different standpoints. And then the judge makes the final verdict. These are 3 specialists, 3 different people altogether looking at or examining the same patient. So the cardiologist is basically going to examine the heart. Radiologist is going to examine, other parts of the body, the liver, the kidney with some scans, and then the neurologist is also going to look at the neurons of the person. Now, the consultant here is doing what we call stacking. The consultant is going to consider all the reviews from the different specialists and then make a final diagnosis. So that is what we call stacking. She doesn't look at the patients. That is the raw data. The patient here is the raw data. She is only combining the specialist opinions of the patient. So this specialist says this specialist says that, this specialist is also saying this, and then make a final decision. Now, what makes stacking different? In bargain and boosting, we always combine the same type of model. We tell you that in bargain and boosting, I said earlier on, we create sub-models within the same model. So it's the same type of model that is addressing issues differently. The same type of model in one that is addressing issues differently. But in stacking, you are looking at different types of models and you train them on the same data sets. And then the meta learner or the advanced model here you are going to use is going to figure out the best way to make the best prediction out of the individual predictions from these models you are looking at. So, like I've clearly explained, maybe I have one data set. I use a decision tree on that model. I use logistic regression. I use SVM. 3 different models on one data set. Now I'm going to introduce an advanced model, which in this case we refer to as the meta learner. So more like the mediator, make the final verdict. So this meta learner is not going to learn or from the data set, the raw data set that was given. It is only going to look at the responses or the predictions of these different models, bring them together, and be able to also make a prediction out of what has been presented to it. So it's like different models have shared their opinion, and I am going to make the final verdict out of the opinions that have been shared. So basically how stacking also works, you choose diverse base models, train each of them, create a new data set from the predictions. Then you train the metadata on this prediction. So the metadata is not going to learn from the original data set, but the predictions from the previously trained data set. And then it's also going to predict on new data sets through the entire pipeline. So it is learning from what you've learned. So more like you went to school to go and learn maybe data science. You learned, and then I take 3 or 5 learners from your class, tell them to teach me data science. What they teach me is what I'm learning, not what you were taught in class. I don't know how you studied for yourself, but what they teach me is what I combine together, and then I'm able to also, let me see, get myself abreast with data science and find my way around it. So in the end, I'm making the final verdicts based on everything that I have learned from you. So I think these are the 3 principles I wanted us to touch on this evening. I don't know if anyone has any questions for me, then we can take it from there. So let me pause here and then open up for questions on the 3 techniques in advanced machine learning models and ensemble basics. Any questions so far? David and Alvis, I think I would want to pause here and then open up for questions. So, any questions?
Okay, so please, if you have any questions for our resource person, you can share it in the chat box or mute and speak as well. So if you have any questions concerning what you are doing today, please unmute and speak or share your question with us in the chat box.
It looks like we have the best of students here, so no questions for us. I mean, no questions for me for the night. When there are no questions asked in the class, is always 2 things involved. Either we didn't get anything that we talked about, or we totally understand. So it's either overfitting or underfitting. So where do we stand? Maybe I should hear from each one of us. So you answer where we stand and then what you are taking home from this meeting. So Edu Jemfi, Evans, Frank, Forsen, any one of you can go first, but I guess everyone will speak. So let's round up with that. Have you been overfitted or underfitted? And what are you taking home from tonight's meeting?
Okay, so what what I've learned this evening is that the advanced model, there are three types. They're bagging. So the bagging will let your model create submodel based on variations of the data you give it. So with that one, it creates variations, and then the variations work on the data at the same time, but like separately. So they work on the same data, but there are little differences within the data, and they all work at the same time to give you a result. And the boosting works one at a time. So it takes the first one, it works on it. Then with the mistakes it made, the second submodel will work on the first one's results and then improve on it. And it
Okay.
keeps doing that till it's done. And then the last one, the stacking. That one is like when the data produces when the model gives the like different models to work on the data to give answers. And then the main one will look at those answers and then sum it up to give you the prediction or the answer that you need at the time. Yeah, so
Okay.
that's how I understand the theory of them.
All right. Thank you for sharing. Who is going next? Let's round up. I think we have Frank, we have Forsen. Let's hear from you. Okay, I think I want to believe they are not able to speak at the moment. So Elvis and David, I think over to you again.
Okay, thank you, Mr. Eric. Ayitey. Please, I want us to appreciate our resource person by reacting, or if you can also unmute and speak. And
Yes,
thank
a
you
big
for.
thank you, Mr. Eric. Big thank you, big thank you, big thank you,
Oh, thank you too.
big thank you, big thank you. Hey, David, somebody signed this up.
Yeah, I think that's Frank. So Frank, please, if you are there, you can
Oh,
unmute and
okay,
speak.
okay.
So, Mr. Eric, thank you very much. We appreciate your time. So, I've also learned a lot from today's session. And some, please, I think there is noise here. Let me stand there. Hello. Hello.
Yeah,
Yeah,
Frank, we
no,
can
we
hear
can hear
you.
you.
Okay. So, we learned a lot today. And some of the things that we learned were that is the methods, that is the ensemble basic methods, that the models that we have. We have the boosting, we also have the stacking, and then bagging. So I learned that the boosting it works sequentially. It takes models and works sequentially. Whereas the bagging works take models and that is train them parallel in, let me say, parallel format. And then the stacking collects other models and then draw let me see results from it. Yeah. So that's basically what I understand so far.
All right. Thank you,
Thank you.
Frank. And that's basically what we talked about so far too. So thank you for your time as well. I actually really appreciate the opportunity. I mean, despite the rain, I couldn't afford to disappoint Elvis the second time after the first one. So, thank you all for your time, and I really appreciate joining you. Maybe I'll also join subsequent sessions if possible to learn from others. I mean, we are still learning. Elvis and David, thank you.
You're welcome, Mr. Eric.
Okay.
We might see you again in maybe subsequent meetings as well.
Sure.
So please check the chat box. There's an evaluation form there. I want you to help us fill the form in order for us to make amends in our next session as well, so that we can prepare adequately. So kindly check the chat box. There's a link there for you to access it to fill the form. Also, our next section will be a Zindi challenge sprint and project work. So during the week, we'll posting our videos on the previous sessions so that if you missed, you could go back and watch them and catch up in preparation towards the Zindi challenge sprint and the project work. Also, I want to encourage you to also share the link to your friends, your colleagues, to also join us in our upcoming sessions. Yes, share the link. Do not be the only partaker of this bootcamp or this session. So when you are joining, invite a friend, share the link on your status in your groups as well. And I think that will be helpful to someone out there who is into machine learning or into the tech world. Yes, so thank you all once again for joining. Thank you, Edu Jenfi. Thank you, Fosun. Thank you, Frank. Thank you, Evans. And thank you very much.
Thank you to.
Thank you.
Thank you to.
So please, our time is fast spent. We end here and meet in our next section. Everything we communicated on Telegram page. So please do well to check on our pages as well. Also watch our videos on the YouTube channel. Like, subscribe, and share to your colleagues. Thank you for joining, and do have a good night. See you all next time.
So,